on the slide right now is that you are asked to watch videos. I do put some of that content into the lecture slides. I try to minimize that as much as possible so that you're watching it online and not in here. But some slides like this are a really big, useful review slide, so I want to kind of overemphasize it. The note to myself is the title. If the title's in red font, I know that's something you've already seen. Okay? So to me, that is now something that I shouldn't have to discuss in detail because I'm assuming it was discussed already. So when I see that, what I'm trying to now signify is what did you have questions about when you saw this? And if you don't have questions about it, then theoretically we can move on. Does that make sense?
Yes.
Okay. So within this, what this is summarizing is all of the reactions you're responsible for. I will say one adjustment. This slide actually has the combustion reaction written on it, the general format, which wasn't in the play posit. Okay? So the combustion reaction is now up here. You are responsible for looking at any chemical equation and being able to map it to one of those categories. Okay? Or as Greg would like to refer to them as genres. These are now genres of reactions. You have to be able to recognize the patterns of that genre to be able to nail down which one it belongs to. Why do you need to know which one it belongs to? Well, one, it's a labeling system, and two, certain genres have more requirements. Okay, for instance, in most academic classes, right, would you expect the poetry genre to show up in your English class?
Yes.
Has it shown up at all in this class? Did it show up in English 101?
Yeah.
Yeah, actually it did.
Well, some people yes, some people it didn't. Okay? That genre may or may not appear. How about comic books?
No.
Right.
Yeah.
Unlikely. Why is it less likely? Right? There are certain aspects about it that you just aren't responsible for. How about an academic essay? Yeah, that showed up everywhere because you were required to write academic essays. The expectations behind that are higher. So when we're looking at these genres, the expectations for those four are higher. The expectations are that you are able to predict each of those. So that if you are given just the reactants, you should be able to predict what the products are. Okay? So you have higher expectations for those last four systems, which means you have to be able to look at an equation and be able to decide how does it match to those patterns. Make sense? Okay. So we'll look through all of those, starting with our combination. Okay? I really do need to rework the combination in the decomposition slides because particularly how the textbook formats it is it makes it look like you're expected to predict products. You are not expected to predict products. Just because you're not expected to doesn't mean you can't. Does that make sense? Okay, so let's take a look. Magnesium metal reacts with oxygen gas to produce. Okay, you are expected to be able to translate the English language into a chemistry expression or a chemistry equation. Okay? So that means nomenclature. So let's start this process, which I believe is one that was on the play posit, but let's see. So magnesium metal.
Yes.
What is that symbol? Mg. What else do we know about it? How do you know it's a solid? Kind of accept it's a metal. There we go. When we look at the periodic table, its font is black. Black meant solid. Reacts, of course, I keep screwing that up, with oxygen gas. And so we would write oxygen and gas. O2. Why do we know it has to be O2?
Because oxygen is negative 2 charge.
Oxygen has nothing to do with its negative 2 charge, and that is one of the things that gets misleading with oxygen. The oxygen here is neutral, not charged. When we're looking at our chemical reactions, everything goes in neutral. Okay? If it was a negative 2, we'd see that in the upper right-hand corner. It has nothing to do with the 2 as a subscript. What is the subscript reference? The number of oxygen atoms. So why is oxygen gas O2? Is it one of those weird special things? Yes. Yes. It is a diatomic element. You are required to know that oxygen, whenever we reference it, should be written as O2. What if I want it to be just O?
Then you
Not quite. What if I want it to be just O?
We'll put an H.
H would be a hydrogen, so that doesn't work. If I want you to write just the letter O, I need you to say an oxygen atom. If you don't see that word atom, it has to be O2. Okay? This now produces. Okay? Well, if this is a combination reaction, I have to combine the magnesium with the oxygen. So what product should we get? Mg, and then I hear O2. Why did you say O2? Because there's two oxygens on the left-hand side. So if I'm going to make water, H2O, right? What elements come together to make H2O? So then that equation must be invalid. I need to do H2O2. Is that water? No, that's peroxide. Okay? So what does that 2 mean? That 2 is in reference to the number of atoms for that species. Okay? If I'm going to put a 2 there, I'm saying I need 2 oxygens in magnesium oxide. I don't care how many I started with. That is entirely irrelevant to the system. Okay? I have to make sure that if magnesium oxide is made, it has to have 2 oxygens. Well, how do I decide how many oxygen magnesium oxide should have? I would have to evaluate the charge of each of the pieces. Okay? This is why nomenclature is important. Okay? Nomenclature is important to recognize the balancing of charges, not the actual name. Magnesium has what charge? A +2. Oxygen has what charge? A -2. How many oxygens do I need to balance out the magnesium? 1, which means writing MgO2 is now false. It has to be written as MgO. Kind of make sense? Okay. And so we have to be very careful with when we shift numbers around across the equation. You have to know why you are placing them there. Okay. This may introduce the next question behind it. Is this equation balanced? No. Do we need to balance it? Yeah, you should always work with a balanced equation. Okay? So how do I balance it? I have 1 magnesium, 1 magnesium. I have 2 oxygens, 1 oxygen. Parentheses around the oxygen, isn't that the same thing as just saying MgO2? Okay. When I'm balancing the equation, the numbers I'm changing are not subscripts because that's changing the compound. What do I need to change? The coefficient in front. Okay. So now I would have 2 oxygens on the right-hand side, which is great. So now what do? I start again. How many magnesiums on the left?
2.
Left is 1. On the right? 2. So now how do I fix it? I need a 2 there. How many oxygens on the right?
2.
Oxygens on the left?
2.
2. What should I do? Check it again. Okay? And it is fine for you to be like, oh, it's balanced. I understand that you're internalizing that last step. For practice, don't internalize it. On the exam, you're okay to internalize it. When you get it wrong, I'm going to be like, did you actually do that last check? And you're going to be like, well, I did in my head. And I'm going to be like, you got the answer wrong. You should have written it down. Okay? So, if we go back, Mg2, 2, 2, and 2. Yeah? Make sense? Okay, so that one you could predict. What if I'd gone through and I'd said, of course I don't have the example on there. Let's pick iron with oxygen. Okay, well, what's the symbol for iron? What's the symbol for oxygen? O2. Okay, to produce... Well, the iron with the oxygen, right? Okay, I need to know the X and the Y. How much iron do I need to balance out the oxygen? Well, I know the oxygen is what charge? -2. What's the charge on the iron? It could be +2. It could be +3. Do you know which one it is? we would have to solve for it if I was given more information. I'm not given more information. I was just told iron with oxygen, which means, can you predict your product? No, this is why we don't predict combination reactions. Because there's certain cases where you can do it. There's a lot of cases where you can't. Okay? Those lot of cases make it not worth the effort to say you're responsible for memorizing them or knowing how to do them. Okay? Does that make sense? Decompositions are similar, okay, in the process that you don't have to know how they decompose. You just have to know how to balance them out. Okay, so you're still responsible for the nomenclature behind it. How do we convert the English language into a chemistry expression? So, real quickly, what are we starting with? Mercury 2 oxide. Okay, so, and I started to do an interpretation when you just gave me the English language. So first we need our symbols, our chemical symbols. So mercury is Hg. Our oxide is O. Is that formula correct?
Yes. No.
What is the charge on oxygen?
2. No.
What is the charge on mercury? Is our formula correct?
This
Yes.
We haven't dealt with the state yet. Is the formula correct? Yeah. That formula is properly balanced. Did I forget the phase? Yes, I did. This is something that I personally have a very hard time with specifying. This is why one of the big reasons why I don't teach 151 and 152, because I'm not consistent enough in specifying phases, and it is of critical importance to always specify your phases. Okay? And because I don't do that consistently, it makes it challenging because I have to keep doubling back to include phases.
Does that have to do with your specific focus or background, like your area of expertise?
Some of it has to do with my background, my preferences in organic chemistry, and we rarely specify phases in organic chemistry. Okay? In general chemistry, it's important because how do I know a chemical reaction has happened? A change in phase. So if my chemical equation doesn't show the phase, how do I know a chemical reaction has happened? I'd have to be looking for some other piece of information. Okay? I would have to have a deeper understanding of the chemistry, which I do, so I cheat and don't show the phase. Okay? You don't, so putting me teaching that then becomes the problem. Okay? So mercury oxide decomposes. Okay? So that's going to have to decompose into something. So it's going to have to split into two pieces, at least two pieces. Okay? So what would those potential products be? Mercury and oxygen. For this one, it's a relatively simple one, so we could predict those pretty quickly. Okay? But again, that's not the expectation. Okay? So let's throw out another one here just to make it more difficult. Potassium perchlorate. Okay, what is its decomposition? So, potassium is K, perchlorate, ClO4, okay, which, for the record, you're not required to memorize. Okay, perchlorate's not one I expect you to memorize. Okay? If you've got it, great, and I would have just given it to you. Okay? What is the charge on potassium?
1.
It's a +1 because it's in that first column. Perchlorate, some people knew what it was to begin with. What did you get? -1. Yes, it's a -1. Okay, so potassium perchlorate, that formula is correct. What does this decompose into? Okay, this becomes a much more challenging one. Again, this is why you aren't expected to predict decompositions. You actually know this one because I gave it to you already in class. Okay? And I don't expect you to know that. Okay? What I would expect you to be able to do is to predict that and balance all that fun stuff out. Does that make sense? Is that equation balanced? No? What's wrong with it? The oxygens aren't balanced, so we could go through potassium left. 1, potassium right. Cl. 1N. 1O. And what do we need to do? And now it becomes balanced, yeah? Makes sense? Questions about that? Okay. So again, decomposition, you need to recognize the pattern. When you look at a decomposition, how do you know it's a decomposition reaction? What about this equation told you it was a decomposition? You started with one piece and you ended with more than one piece. It doesn't have to end in two necessarily. It typically ends in two, but it doesn't have to end in two. Okay? What if you were given the word equation? How would you know it was a decomposition? It usually says decomposition in it. Okay? So there are tip-offs behind those. Does that kind of make sense? So those are the patterns that you're trying to look for. Remember, your formulas may look wildly different. Potassium perchlorate had 3 different things in it, where we had mercury oxide only had 2. Okay? So the composition of those individual pieces of what's being labeled here as AB could massively change. So don't overemphasize that. That's why when we look at those patterns for those, it's just saying AB all in black. There's no color specificity to it, because the color specificity we can't really overlay cleanly. Yes?
I guess I do have a question about why it doesn't break down into potassium, chlorine, and oxygen.
So the specifics of why it doesn't break down into those pieces has to do with the stability of the individual atoms involved in it. That why is a question that's outside the scope of the class. So, sorry.
That's okay.
Dodge. Okay, so double replacement reactions. Okay, so when we go through and look at the double replacements are going to add a whole nother can to this, okay, or a level of difficulty. You are now required to predict them. So you have to be able to look at a word equation or a chemical equation and predict what the products are. So something about how those reactants are written should set off alarms that it is a double replacement, such that you can do the prediction of the products. So what about both of those reactions gives you information that they're double replacements?
Because it says where
Yes, twice.
and then it has like
Right? Phases aren't necessarily tip-off. Phases could be helpful, right? Because in our combination had 2 pieces, right? But those phases could be solids, liquids, and gases. Here they're going to be all aqueous. So that phase could really help out. Okay? That phase, interestingly enough, wasn't specified in my earlier general format. Okay? But way to jump on the phase. That's a good thing to look for. What else could we be looking for?
There's 2 chemical formulas.
2 chemical formulas. In a combination reaction, how many reactants did you start with? 2 chemical formulas. So yes, 2 is a piece, but it's not the whole puzzle. Okay? It's not that there's 4. There is a particular characteristic that I know where you're going when you're calling it 4. It's not that there's 4.
Oh, the spreadsheet? No. You can't see that in the written word, though.
It's a metal and a non-metal. So what we're referencing is not just that there's 2 pieces, it's that there's 2 pieces and that each of those 2 pieces are ionic, such that we have 4 things that we're allowed to manipulate. Kind of make sense? Okay, so we've got the 2 equations up here. Should we do it as a race? No? Okay, not a race. Okay, a race for you guys. This side of the classroom over here, you guys can do the orange equation because there's more of you. This side of the classroom over here can do the purple equation. Okay? Come through with a full equation. Talk to whoever you want to within your group to try and get those equations figured out. I know. If you've already written it in your notes, go through and rewrite it. Resolve it. Don't look at your notes. Practice it. Or point out some pieces of information. And a name. If you see that second species come in with an id, with a D, that's a general, I'm calling it a white flag, okay, for a binary ionic compound. Okay? So if you see that D there, that's typically a reference of a binary ionic. Okay, or really it's just a reference for binary because we have our covalent compounds or binary molecular. Okay, we know it's ionic because barium is a metal. Okay, so it's binary ionic because we see that D. It's not a guarantee because hydroxide and cyanide both end with that IDE ending. Okay, and they are misleading because they are ternary compounds. If you see the T in the ending, that pretty much instantly means it's ternary ionic. Okay, which means you're looking at a complex ion. Okay? So having that piece of information from your nomenclature rules can help you build that out. Okay? You guys have already started to put together the equations for these, so instead of actually working through them all, what we're doing is just going to jump to the answers. Okay? For the left-hand side of the classroom, they did a really good job putting together the individual pieces. Okay? They had the individual compound formulas correct. They even balanced the equation, which I did not do in this case, because what do we need?
2 KCl.
We need 2 KCLs, and now the equation would be balanced. But the part that was universally missed on the left-hand side was acknowledging what phase the products needed to be. Okay? The reactants should be obvious because they're in the statement. Don't start dropping. If you're given the phase, you should specify it. Okay? We got close with the phases, but not perfect. Okay? So we would have to specify that solid and aqueous. Well, to know that, we would have to have some more information, and we'll address that in a second. For the second equation, it was a little bit simpler, okay? But then we had the second equation, which came out balanced to begin with. Okay? We still have that IDE versus 8, or that T ending, coming in with our complex ions. We're doing the double replacement, so everybody was getting the double replacements down, which is nice. It looked like we're doing okay with the balancing as well. Okay, the phases become trickier. Notice that in the second one, what is interesting about those phases? Everything is aqueous. Okay, so let's add a whole other thing on this. We're supposed to be able to predict what the reaction is.
That's why I know it's allergies. It's a
Dude.
sneeze.
Interruption? Much?
What a jerk I am.
Next
Predicting.
Never. I'm just going to stop. Predicting. If we go through, we were able to predict those individual products after doing the double replacement, but we should also add another layer on top of that. We're assuming, in this case, that a chemical reaction has happened. Did a chemical reaction happen for the first equation?
Yes.
Yes. Did a chemical reaction happen for the second equation?
Yeah.
No.
Ooh, now we got reacts in quotes, which should be a red flag that something weird is going on here that we might need to look a little bit closer.
The statement
Okay.
changed.
I'm loving where you went with that. Fantastic. To decide if we have a chemical reaction, we have to know what dictates a chemical reaction. Phase change, color change, temperature change. When we're looking at equations, okay, in a test, the energy change, temperature, or color change are not going to be things we can see easily on a test. The one thing we'll be able to see would be phase change, which is why it's really important to specify the phases. And when we do that, for that first equation, we start with 2 aqueous and we end with a solid. That is a physical or a chemical change. So that's a chemical reaction. What happened in the second one? There's no phase change, which means no chemical reaction. Even though we've exchanged those ions, that actually doesn't matter. There's no phase change.
So what kind of change would that be? Would it be physical change?
It's a physical change. You just mix 2 solutions. Woohoo! Right? That's it. Okay? So to those phases, how are we supposed to know what phases should be associated with these? How do we predict those? That is not something you are required to memorize. It is something you are required to manipulate and use and reference. When it comes to homework, you should have a table of solubility rules provided, okay, or available to you. Your textbook gives you this list. It's straight from the textbook. Okay? When it comes to the exam, I do not expect you to memorize really any of these, though there's some slight exceptions on that we'll talk about. And slight because it's recommended that you memorize, but not a requirement. Okay? We need to be able to manipulate and use this table. So how do we do it? Let's pick the first one, barium chloride. Okay? For that compound, how do I know it's aqueous? I'll accept two answers. It said aqueous in the statement when we wrote it down, right? Okay, so cool, that's fantastic. How do we use the solubility rules to figure out that it's aqueous? Just how? I see you doing something. Tell me how you are doing it. What are you doing? Just reading the rules?
Looking
Trying to
for
apply.
compound
So ultimately, it's not just reading the rules, because ionic compounds containing the following ions are generally soluble in water was a useless thing to read, or maybe a useless thing to read.
You were looking for where BA and CL.
I'm looking for, in particular, BA and CL. Once I found where those are, now I can reference the rules accordingly. So we can go through and start underlining where we see these things show up. Right? I think I got them all. So there's 4 cases. Of those 4 cases, is any one more relevant than the others?
4,
Okay, why is 4 the most relevant?
because there's BAs attached to like the S and the OH and the SO, and we don't have that.
When we look at rule 5, that is barium with sulfate. It's not with sulfate, so I don't care about rule 5. If I look at rule 9, it's attached to sulfide. I don't care. It's not connected to that. Rule 10, OH, I don't care. Okay, which means the only rule I need to look at is rule 4, and that says halide ions. What the hell does that mean?
Is it like
Now it's worth referencing the heading of that. The heading says compounds containing those ions are generally soluble. So generally should freak us out a little bit, but conveniently, what's in the table? They give us the exceptions. Okay, so generally, if we see a chloride, it should be soluble. What are the exceptions? Silver, mercury, and lead. Is barium silver, mercury, or lead? Nope, which means it's soluble. What should the phase be if it is soluble? Aqueous, not S for soluble. Okay. The S was for solid. Okay, so you got to be careful with those referencing of those labels. Okay, so soluble is aqueous. So what would we specify next to it? There it is. Aqueous. Let's look for one that doesn't come out as aqueous, barium chromate. Okay, so the same process, we want to look for barium. Wherever barium shows up. And in particular, what else? Chromate. Which rule should we be looking at? Rule 7. I don't care about the other ones because they aren't referencing barium and chromate. Okay? And it says 7. 7 is now in reference to the heading above it. What is that heading above it? Generally insoluble, which means they did not dissolve. If they did not dissolve, they are solids. Okay? Are there exceptions to that rule?
Yes.
Damn. So we got to look at the exceptions. The exceptions reference Rule 1. So I got to go all the way up to Rule 1. And what is Rule 1? Alkali metals and the ammonium ion. Is barium an alkali metal?
No.
No. Is it an ammonium ion?
No.
No. So the exceptions aren't relevant. Which means the phase for that one would be solid. There it is.
How would you know if it's a gas?
Say that again?
How would you know if it's a gas?
The phases other than aqueous or solid are common knowledge.
Okay.
Okay? So if I wrote CO2, what would you say the phase was? Gas. Okay? Right? Theoretically. Okay? If I wrote C2H6, how do you know it's a gas?
It's a guess.
Okay?
Is it because it
That's not common knowledge. Since you don't know that, you wouldn't be asked to specify that phase. C2H6 is ethane. Okay? If I gave you methane, a lot of people would probably have told me that one is a gas. If I gave you propane, you probably would have told me that one was a gas too. Okay? Ethane's right in the middle. That's probably missing everybody's common knowledge spot. Right? So the phases outside of aqueous and solid are common knowledge things. Really, you see CO2 as a gas, and you see H2O as a liquid. It doesn't make sense to call H2O aqueous. Remember, aqueous means dissolved in water. It doesn't really make sense to say water is dissolved in water. Okay? Kind of makes sense? Okay. So within these, I said you don't have to memorize. You are required to use them. If you take a look at practice exam 1, I do give you a condensed table for predicting phases. Okay? So if you take a look at that cover page, it's already there. I did say, however, it might be useful to memorize some of these. I have some of these memorized. Any ideas which of these I have memorized? Rule 1, yes. Rule 1 is memorized. Why might I memorize Rule 1? It generates lots of exceptions to the other rules, right? So if I have Rule 1 memorized, I now have a lot of the exceptions also memorized. What else?
Number 2.
Rule 2. Okay, don't answer the why yet. And? Rule 3. Why would I memorize those 3 rules?
You're supposed to memorize compounds.
Why would I memorize those 3 rules?
Acids.
What's that?
Because they're acids?
Nope. Commonly used isn't necessarily a bad thing, but no.
I'll just say because you said it, you play possibility of memorizing.
Okay, but why would I say to memorize them? Why are those 3 things that I have memorized?
Because they'll be useful on the test.
Potentially.
Part 2.
What is different about rules 1, 2, and 3 versus 4, 5, 6, 7, 8, 9, and 10? There are no exceptions to rules 1, 2, 3. That's why you memorize them, because they're guaranteed to be right. Okay? Minimize the amount of effort you have to do, not maximize. Does that make sense? Okay? Which is that's a counterintuitive statement, right? Aren't you supposed to maximize effort? Right? Scientists, lazy. Minimize the effort.
Maximize productivity.
Okay? Maximize productivity. Does that make sense for solubility? We good?
Yes.
Okay. So, neutralization reactions are really just a special case of double replacement. They match the exact same pattern. Okay? Why do we reference neutralizations as independent reactions from double replacement? What about acids and bases? So neutralizations, yes, involve acids and bases. How many of you were wary of acids before you started this class? Wow, you've all heard of acids before this class, and not the psychedelic kinds. Right? They're dangerous. They're reactive. Acids and bases are probably the oldest category of reactions. They were probably the first determined. Neutralization is effectively a historical category, giving weight to what we already know for common knowledge. Okay? So it's a special category of our double replacements that are very specifically looking at acids and bases. Okay? So it's the same process. But because it is very specifically referencing the presence of an acid, H in front, and bases, which we'll define much later in the semester, OH in back, because it has those 2 pieces already defined, we know that one of our products will be HOH, also known as? Okay, it's okay. Don't stress. Sometimes the way we format formulas makes it difficult to understand the information written there.
Oh, water.
It's water. When we're doing a neutralization reaction, it's the production of water. Okay? And we'll open up that argument on hydroxide much later in the semester. So we end up with a salt and water in all neutralization reactions for this class. Okay? Make sense? Okay. So there's an example. Notice that we have water. We still have to predict that phase. That's that common knowledge one. We would have to know as a liquid. Okay? And I conveniently didn't balance this one either. To balance it, what do we need?
2 in front of H2O.
2 in front of the KOH and a 2 in front of the H2O. We'll need both. Okay? The last reaction type, combustion reactions. Again, these fit a very narrow category. Okay? Again, for the sake of this class. We're taking carbon and hydrogen in some number amount. Don't stress on the specific number amount. Okay? But we're taking that compound. We are reacting it very specifically with oxygen gas. Regardless of the numbers of carbons and hydrogens, we will always end with CO2 and water. Every time. Okay?
What's the balance?
The equation is not balanced. This is one I'm going to leave to you to balance on your own spare time. If I picked the proper equation, you should have trouble with it. Okay? So, and I'm giving it to, because you need that practice to be like, well, wait, it didn't balance. You need to work through that process of figuring out how to balance it. I have no problems helping you outside of the class, but that is something you just need to be aware of. I want you to kind of struggle with that a little bit. Okay? We've got enough content that we have to get through that unfortunately I can't drag to look at that balancing. Okay? And no guarantees it's actually one that's supposed to be a challenge. These are a lot of practice. I have no problems doing this practice, but I really want to push that practice to actually next week. Okay? Because if we do our time on it now, you'll be good at this practice, but then we won't have covered the content for the semester, and that would suck, because if you don't get 10% of the content, the highest grade you could get would be a 90% in the class. Okay? So we'll come back to that practice later. Okay? Which then means we have this big, massive jump to now looking at math. Okay? Yay, everybody's favorite.
This is another form of language.
Okay? So, we talked about powers of 10, right? Okay, and those powers of 10 have certain prefixes. Okay? So that should be good. And we said there were certain prefixes you should memorize. Kilo, centi, milli, yeah? Okay. Did we do this? Yeah? Okay. I heard a yeah and a no. We did? Okay. Okay.
We didn't grab it.
The next part is then the fractional notations. So we've got English language of what we can do with this. There are 1,000 meters in 1 kilometer, yes?
Yes.
Mathematics can take that and say 1 kilometer is equal to 1,000 meters. Right? So we've simplified things down a lot. Okay, well, why is that useful? Okay, so that doesn't make it useful. That just explains why we've shortened it. Why would that be useful?
You don't have to write when the scale gets larger, you have to write how it's that much.
Easier to memorize.
How is it 5,200 kilometers? What did you do to come up with the answer 5,200 in fact, meters, not kilometers? You multiplied by 1,000. Everybody agree with that?
Yes.
What happened to that km?
Oh, it's, I don't know.
Well, you transferred it 2 meters, so K is no longer needed.
That km, you did nothing to. Which means if this is a proper equality,
No, we got,
and that's a false statement, right? So you did something to that km. What did you do to that km? It's not just that I multiplied by 1,000. I actually did something else that you have internalized because you've run that calculation a whole bunch. That's awesome. Stop freaking internalizing it. Okay? You need to write out that conversion process. Where is that conversion process coming from? And so what we're really trying to get at is the intentionality behind those conversions. Okay? And this is a challenging area for everybody to deal with, so please kind of bear with me. Everybody will go through and will be like, this is stupid, why do I have to show my work? You don't have to show your work for this kind of a calculation theoretically. The problem with it is that if you don't show your work, you don't actually acknowledge that you know what's going on with it, so that when I change the conversion to something you know nothing about, you now can't do the conversion because you haven't actually recognized there's a process behind it. Does that make sense? Okay. So what we need to do is understand where that process is so that when those units change to something entirely foreign and we're like, what the hell does that even mean? Like centimeters? Like what is even that? Okay. You have a process by which you can, that was like an American metric, fine, whatever. Okay, you have a process that allows you to do that conversion consistently correct. Does that make sense? Okay, so, and it looks like you're dying to tell me how to fix this.
Yeah, is it where you go 5.2 km over 1, and then 1,000 meters over 1 kilometer, and then they cancel out?
Okay, so now your kilometers as a unit cancels out. So back to my question, where the hell did you get that from?
The equation that
You got that from the equation? This is an equality. That's not an equality.
It says fraction at the top.
This is the power of our fractional notations. Is this a fraction? How do I convert it into a fraction?
Put it over 1.
Would that be that fraction?
Yeah.
Just dividing by 1 makes that.
You divided by 1
No, yeah, you didn't divide by 1.
What do I want to divide by? I'm trying to get kilometers where?
And your final answer.
Look at what I'm aiming for. This is my target. Where do I want kilometers to show up?
On the bottom side.
On the bottom. How do I get kilometers into the denominator if that is my equality? Divide both sides by 1 kilometer, yeah?
Yeah.
This would get me 1,000 meters over 1 kilometer, yeah?
Yep.
That looks an awful lot like my target.
Yeah.
What is this value?
1.
5.2 over 1.
That value is 1. When you do a conversion, what are you multiplying by?
1.
You're multiplying by 1.
Yes, sir.
That's why the conversion works. If you didn't multiply by 1, your conversion actually doesn't work. Every time you do a conversion, you are trying to decide which one you want to multiply by. What do I mean by that?
See, I've been taught these 2 different ways for 2 different teachers. You're the third.
12 inches, 1 foot, yes?
Yeah.
Is that 1? 12 inches over 1 foot, is that 1?
Yes.
Yeah. What would happen if I now put 12 inches over 1 foot? Isn't this still multiplying by 1?
Yeah, but it's wrong.
It's not wrong.
It's not the same.
Does that get us to the conversion that we're aiming for? No. So when we're running a conversion, our whole goal is to decide what 1 do I need to multiply by. You have to decide what that 1 is. A lot of that decision comes from you acknowledging what units you end with and what units you start with, and establishing those units into the proper places. Once those units have been established into that location, now you can drop in numbers. Right? Which is completely opposite the way you told me to solve. Because what did you tell me to solve this problem to begin with? Multiplied by 1,000. You immediately dropped in numbers. Why? You were used to that calculation so much and so in the past that you have built an algorithm to solve it. What I want you to do is stop using an algorithm and build a process, a rhetorical choice or a heuristic where you are making a rhetorical choice of which one to use. Deciding which one to use can be exceptionally difficult. Okay? That's where practice comes into play with trying to figure out where those conversions exist. Kind of make sense? Okay, so this is where it's coming from. We now have an idea of that process of where we need to go. Okay, a lot of the conversions you were being asked to do in this unit, you'll be like, I just multiply by 12. Okay, what did you do to just multiply by 12? What were you doing? You're like, I have no idea. Why would you just multiply by 12? What were you doing? You were converting feet into inches. Okay? Don't focus on the math. Focus on the units, the process that establishes that. Okay? That is a challenging thing to deal with. You guys can do it. You can pull it off, and you'll be fantastic at it if you focus on the process. Okay? Don't focus on the numerical answer. Okay. Fractional notations or manipulations, this is a real subtle one, so don't stress too much about it. 10 to the positive 2 versus 10 to the minus 2. 10 to the positive 2 means that calculation needs to run in the location that it is currently found. Where is that calculation 10 to the 2 found?
In centimeters. Oh, wait, sorry, rows.
Where is it found?
The numerator on the right side.
It's found in the numerator, which means I'm going to run this calculation 10 to the second in the numerator, which means the answer I get is 100. What does it mean to have that minus sign? Run the calculation in the opposite location of where it is found. Where's our 10 to the minus, or 2 found in that system? It's found in the numerator, so where should we run the calculation? The minus sign means run the calculation in the opposite location of where it is. Where is the 10 to the 2 found currently? In the numerator, which means with the minus sign, where should I run it? In the denominator. The plus and the minus are telling you where to run that calculation. Okay? Which allows you to very quickly shuttle powers of 10 up and down. Okay? Which is nice. Right? If you don't like that, that's fine, because we have an awesome device that takes care of that for us. It's a calculator. Use it. Okay? But this is just a subtle thing to help you acknowledge how to shift those things around on where those calculations are run. That is entirely up to you to decide if you want to use that or not. Okay? But that's how we get different expressions or different things to memorize when we're talking about centimeters and meters. Okay? Or kilometers and meters. Okay? And we'll address that when we cross that bridge a little bit later too. Okay? We already addressed that. I do want to talk about our conversion process. Okay? It is a process. Okay? What did that process, or what should that process start with?
Reading the question.
Reading the question. And in the process of reading the question, what are you trying to find?
The value of
The unit.
Unit of what?
authority.
What measurement?
What you're being asked.
What you're being asked for. Step 1 of all conversion processes is to identify your answer. What is your unit that you are aiming for? So when you go through to solve, you should start there. Write your unit with an equal sign to the very far right of your page. Okay? What should the next piece of information be? Let's look at the information given. Let's start with the given unit. Okay? And because this mantra seemed to work so well in past classes, we'll deal with this. Have unit versus want unit. Don't worry. Yeah, it says have. Yeah. Don't stress necessarily, okay, about the English language on that. What unit do you have? What unit do you want? Okay? If those are equal, what do you now have? You have the answer. You're done. Okay? That would be excessively easy, right?
Yeah.
So what has to happen?
Conversions.
You have to do some kind of conversion. Where what do you want to have happen?
Equals 1.
Whatever that expression is has to equal 1, true?
You want the 1 unit on the top and you have.
I want what I want on top and what I want on the bottom. have unit. Yes, this has to equal 1. How do we know it equals 1? That would be some kind of an equality that you would have to know. Sometimes that known value is obvious. 12 inches is 1 foot. Okay? Sometimes it's less obvious. 1 gram of hydrogen is equal to 1 mole. You have no idea where that came from, maybe, at this point. But that information is available to you. You have to be able to tease where that information is. So you have to know where to find that conversion. Okay? What if you don't have that conversion? What if it doesn't exist?
And you work it through.
Okay? You look at it and you're like, well, I know what I have and what I want isn't there. So what I'm going to do is I'm going to convert it to a have to, meaning a different unit that I can put in there, okay, coming from that, which then means the next system is
1 and a half to
want unit, a have to unit. Every time we go through and solve, what you need to identify is what do you want and what do you have. Every conversion process is want over have. Okay? Guess when this process works? Every time. That's why this is neat. You're like, there's no way. Okay? What do you want? I want to become a nurse. What do you have? No educational background. What do I need to do? Get an education. Now I have an educational background. Does that make me a nurse? No. What do I have to do? I have to trade that educational background in for experience to get a license. Now I have a license. Am I a nurse? No. Now what do I need? I have to use that license to get a job. Now that I have a job as a nurse, am I a nurse? Yes. Now I'm there.
Let's go.
That works every way through. Sometimes it's just a few steps. Sometimes it's a crap load of steps. Sometimes those steps are going to be exceptionally painful, like taking a chemistry class. Okay? That is perfectly acceptable. But you have to acknowledge where that goal is. What do you have to go through to get there? Right? And do everything that you can to maximize those conversions to effectively be one. Okay? Because if you treat that chemistry class or that biology class as a loss, what happens? You're no longer multiplying by 1, which means your end goal is no longer as good. Okay? You've decreased the value of your desire from the beginning. Make sense? That was actually insanely deep. I've never done that. Okay, so process as the textbook outlines. Unit that you want for your answer, unit that you're given. Okay? The textbook says given value. I would argue it's not the given value that's important, it's the unit. Okay? Then it's what do you want over what do you have. Okay? And you deal with the numbers after you've addressed the units. That conversion process is tedious, but it will get you to the correct answer, and it will get you to the correct answer correctly, amazingly. Okay? And when? Always. Unfortunately, it does take more time. Okay? I would rather sacrifice a few seconds to get it right than to do it faster. It's not always true in today's society. This is why people get x-rays and they find like a pair of surgical scissors embedded in their body. Because the surgeon was like, I just need to be done. Zip! You left the scissors, dude. Okay? So focus on that process. Okay? This is just kind of funny. So somebody built this comic, right? Okay? And what's extra funny about this comic, because you're like, oh, that's just hilarious because the Americans are doing it wrong, is the comment that follows this. 1 is smaller than 1.6, so it must be right. That's not how numbers work. Okay? You have to deal with the units behind those conversions. Okay? So, classifying chemical reactions, we're going to jump back to our chemical reactions. All of that conversion stuff is back in chapter 2. We will come back to looking at specific examples of that. Okay, but what I'm hoping to get into is some of that stuff I made you watch in that painful redox video. Okay, and address some of that content. Does that make sense? Okay, once we've got that covered, then we're just doing conversions the rest of the class times. Okay? So, we've got combination, decomposition, single replacement, neutralization. See how new the combustion one was? It hasn't actually made it into all of my slides. The only one that's left off so far is our single replacement. Okay, so we need to take a look at that single replacement reaction. Okay, so here we go. I really should fix that. Zinc plus lead sulfate does what? Okay. What tells us that this might be a single replacement reaction?
You have an element and a present.
I have an element all by itself, and then I have some kind of compound next to it. Okay? The default that we'll find for a lot of our single replacements is that that element that's all by itself is a metal, and it will be exchanging with something else where it's exchanging with the metal in that ionic compound. So we're exchanging metals. It does not have to be metals. It can be nonmetals. But it is most commonly found for metals. I believe I threw a nonmetal one into the video.
You said that if it ends in the 8, that it's ternary.
Yes.
Okay, so that would be.
So if we were to name that compound, let's test that theory. Name that. What do we have? We have lead, because a Pb. SO4 is sulfate. Would this be a proper name? Nope. Why does it have to be lead 2? How do I know it's a +2? Nope. Lead is not one you're supposed to memorize. Sulfate is a -2. The lead must be a +2. If lead was one you were required to required to know the charge on, putting the Roman numerals is actually wrong. You are specifying more information than is necessary. Doesn't matter if it's correct. It's wrong. Sorry, it's the way it works. So lead is not one you're required to memorize the charge on, which means you have to specify the Roman numerals. How do we know lead needs to be a +2? Sulfate's a -2, and I have one of each of them, which means the lead must be a +2 to balance it out. That's that balancing of the charge aspect.
Wait. So lead is a +2 and it's not a +4 or something because it's below this.
So, because it's below that staircase, you shouldn't be memorizing it. Carbon, so I know where you're going with that. You're like, oh, +4, -4. Carbon could be either one. No. Carbon could be +4, +3, +2, +1, 0, -1, -2, -3, -4. This is why, for carbon, what did I tell you?
Don't remember it.
Don't memorize it. It could have too many different oxidations or charges. Okay, so don't memorize that carbon one. Okay, for memorizing those columns, what you're memorizing is only for the nonmetals, not for the metals underneath. The metals will change, and that's that line, that staircase is our big switch in electronegativity, which is why we go positive to negative.
Okay.
Okay?
Are we supposed to memorize 1, 2, 3, and then 3, 2, 1, and that's it? Or if you...
So, memorizing charges, because we're back on it. Column 1, +1. Column 2, +2. Nitrogen, phosphorus, arsenic, -3. Oxygen, sulfur, selenide, telluride? I don't think it's telluride. Tellurium? I think tellurium is better. -2. Fluorine, chlorine, bromine, iodine. You'll never see it. -1. Okay? So those you should be able to derive based off of our noble gas comparison. Aluminum, zinc, cadmium, silver are the ones that I say you should have to memorize because you can't derive those easily. Aluminum's a +3, zinc's a +2, cadmium's a +2, silver's a +1. Okay? For the record, those are things that you had to have memorized. How many people memorized those? Okay, that was 4 people in a class of 15. Not a single one of you took notes on what you were supposed to memorize. If I say memorize, you should probably take note of it. Okay. Predictions. Zinc was what? In this case, it's actually not a +2. When it's in an ionic compound, it's a +2. Give me another characteristic of zinc. Give me another characteristic of zinc. Give me the characteristic I'm looking for. It's a metal. Wow, that worked. Look at our lead sulfate. What is the characteristic of Pb? Metal. What is our characteristic of SO4? Non-metal. What are the most similar things in this equation? The metals, which means those are going to switch. Pb comes out. Zinc goes in. Okay? Easiest way to deal with this is to also associate the phases with them, which means when lead comes out, its phase becomes solid. When zinc goes in, that phase becomes aqueous. Did I predict zinc sulfate correctly? What is the charge on sulfate? What is the charge on zinc? How do you know zinc's a +2? Because I literally just told you had to memorize that zinc was a +2. So that formula is correct. What we've now done is our single replacement reaction, and we have predicted what would happen, or rather what could happen. That word is very important, because when we're looking at our single replacement reactions, we will predict what could happen. That does not mean it did happen. Have any of you thought about what you would do if you won the lottery? Yeah, you would wear costumes every day? That's pretty cool. I like it. We're just going to say you would. Does that mean next class period you're going to show up in a costume?
Yes.
No, right? Okay, if you win the lottery. So we have a plan if it's going to happen. A chemical reaction is a plan. Okay, I think that's going to be my goal now if I win the lottery, is to always wear costumes.
Wear costumes to pick up the check so that nobody.
Oh, I see what you're saying. Yeah. Okay, so this is the plan. That does not mean the plan actually happened. To decide if it actually happened, we would have to look for other things. In the case of the double replacement, we had to look for phase changes. We can't do the phase changes here because we're just assuming those phase changes would occur. Okay, that's still part of the plan. So the phase change doesn't help us. So in our single replacements, we need to rely on more information. That more information is our activity series. Okay? And just for the record, we're going to be able to get through activity series. We're not even going to start oxidation and reduction. Okay, so what do we do with an activity series? Well, let's take a look. Zinc and lead. Let's identify them on this chart. Zinc, lead. So zinc is more active than lead. Well, what the hell does that mean?
That is more likely to
Liquid places.
like it's
It is more likely to go into a compound. So when I look at this equation that has now disappeared, where is zinc more likely in a compound? Or where is zinc in a compound? Where it is. It's right here. Zinc, right there. Zinc solid. Is that in a compound? No. Where is zinc solid or zinc in a compound? On the product side. Lead is less active. Because it is less active, it should be less likely to go into a compound. Where is lead not in a compound? On the product side. Does this reaction occur?
Yes.
Yes. That's how we use the activity series. Neat little bit of facts here in our waning seconds. Okay, if we think about, and it's all fictitious anyway, but if we think about our global financial system, it's all based off of, as a fun statement, it is actually based off of the activity series. Okay? It's gold. We use gold to back all of our currencies. Why do we use gold? It's actually not that rare.
The least reactive.
It's the least reactive. Gold is in the bottom of our series. Think about all the things that we use as jewelry. We use gold, platinum, silver. Where are they all? Bottom of the activity series. Which means when I put that jewelry on, what does it not do? React with you. Okay, why do we use those for our currencies? Well, let's flip it. Let's say we picked lithium as our currency. You laugh. Lithium is so reactive that all we have to do is like throw a water balloon at it, and what does it do? It explodes. Where does all your currency go? Gone. That's not a good financial system. So we picked the most stable thing possible to back our entire financial system. That's where we're going with gold. That's why there were value behind those metals. Not because they could do cool things. It's literally because they can't. And that's why we use them. Okay? So with that, we've got to stop. We'll pick up